Sasa. Hello everybody, good morning, how are you doing? Today I feel like a YouTuber now. Please give a thumbs up if you like the video. So, can you hear me? Hope so. If you can hear me, send message on Slack so I know you there. Okay, so someone is there now. Okay, so welcome to this new lecture in the module Architecting and Design. So last week, on Wednesday, during last lecture, we discussed about what is design and how how important is the design. So today we start our journey. And we start from the architecting. Okay, so software architecture, as we will see, is the first very important step towards so having a good design. So a design that achieve good quality. Okay. Yeah. I see some of you has problem with the sound. I hope it gets better because it's out of my control actually. So software architecture. first of all, let's introduce what the software architecture is and why it is very important, and then we will go through so how to create a software architecture and what type of concerns, design concerns we have to take into account. So architecture. Architecture, as you might know, plays a very important role, a central role, I would say, in building construction. So everybody know about building construction, more or less about building construction. And an architecture in building construction describes how so different perspectives of the building, and when each different perspective address a specific aspect. So we have an architecture for electricity, we have an architecture for the plumbing system, we have an architecture for the structure of the buildings, so the walls, the different rooms, how the rooms are connected one each other, where are the stairs and the lift, and so on and so forth. So without a good architecture, we are almost impossible. It's almost impossible to have a good design for the building. Okay, so essentially, it happens the same when we talk about software architecture. Okay, software architecture is the process of designing the global organization of the software system. So if we make a bad architecture, so then the organization of the software system will be very bad, and all the quality concerns that we were talking about cannot be fulfilled. Okay, so and in particular, the software architecture will allow us to first divide the software into subsystems. We already mentioned how much important it is to split the big problem into a set of small problems and then address these small problem in isolation. Okay, so the software architecture will allow us to split the big software into modules or subsystems, and then implement the subsystems in isolation, and then to recompose these subsystems at the end. Okay, that's very important. Will allow us to make decisions about how these subsystems will interact each other, what type of data they will exchange each other, how the different operations flow within, so in between subsystems, and very important, how they interact. I mean, the set of methods or services that every single subsystem provides to the others, what type of input they are expecting, and what type of output they are providing. Okay, so the architecture is the core of the design. That's why we start our journey into the software design from here, because if we make a wrong architecture, we will make a wrong design, and we will implement a very bad software system. So the architecture is this place that where we state all the constraints for the efficiency, reusability, and maintainability of the system. It's here that we will get very important decisions. And if we make the wrong decision here, then this decision will affect all the different, all the next steps and all the different choices that we will make later on during the, while walking the design space. You remember we talked about design space during the last lecture. Okay, so then let's deep into this software architecture. I mean, you will have another course later on in your studies, which is specifically about software architecture, and then in that course you will learn better about software architecture. We will not go so in deep in this course because we are focusing on something else, but we need to understand what is a software architecture and how to use basic things about software architecture. Okay? So let's start with some definitions. So what is a system? We already used this word many times so far, but what is a system? So a system is an entity that might be logical or concrete later on, having a set of responsibilities or objectives and consisting of hardware or software. So a system can be a set of hardware pieces touched together, or can be a set of software modules that works together, or can be software that is managing and controlling hardware. Okay, we can have usually we have both. Okay, when we talk about software system, because a software system is usually run on hardware. Okay, then we cannot forget that we have hardware under our knees. We always, as said many times, we always start from the requirements. Okay. So here the requirements is very important, because if we don't have a requirement elicitation, if we don't have requirement specification, we don't know what are the responsibility of the system. Okay, that's so the requirements is always our starting point. Make the requirements for the system, then provide us what are the responsibility of the system, what are the goal and objectives for the system. As said, introduced, mentioned before, the system can be implemented by a collection of subsystems. Okay, so still the idea is to divide the big system into a collection of subsystems and then implement the subsystem in isolation. But what is a subsystem? Yeah, the subsystem is just a system which is part of a larger system. Okay, and which has a well-defined interface. So interface is another very important point here, because the interface is the set of functionalities that every single subsystem expose to the others. Okay, so remember we already talked about information hiding. Okay, information hiding is very important for us. I mean, for the customer. The subsystem or a system is a black box. Okay, they cannot watch inside the black box. The only things that they can access and understand is the interface of the system. It means the set of services provided by the system, together with the set of input parameters and the output results. Okay. Then, since we want to design a software, then we can also talk about module, okay, which is a subsystem. Okay, that is defined at the programming level language, programming language level. And since we are talking about Java, we are Java developers, so a module can be a class or packages or also methods. Okay, these are all modules. So a module is a generic way to talk about a set of methods, classes, packages. So, but why this is very important? Architecture, as you can see from the picture, is really at the center of the development. Okay. Still, we have requirements. It's the very central, because we don't have any problem to solve if we don't have the requirements. Once we have the requirements, we can start building the software architecture around the requirements, because now we know, thanks to the requirements, what we need to implement, and then we start our journey from software architecture. So once we have the software architecture, we can create the software design, okay, which is more low level. And finally, we can start to coding, okay. And this is the journey that we will go through in these next lectures. Today is software architecture. Next week we will focus more on software design and code. We need to develop a software architecture or an architectural model of our system in order to enable enable everyone to better understand the system. We already spent some words during last lecture to say, okay, how much is important is to let everybody working on the system to understand the system. Because if someone is not able to understand the system, will make some mistakes that will affect the quality of the overall system. This will allow people to work on the subsystem in isolation. So the final idea is to create small teams of developers, and each team will implement a single subsystems, and then we can recompose these subsystems in order to work each other through the interfaces. Okay, so another team, in order to integrate different subsystems, what you need to know is just the interface of the system, of the subsystem that you want to interact with. And this will also allow us to prepare for extension of the system. We already discussed about this. I mean, how important is to accommodate future extensions of the system. Okay, the system will be modified sooner or later because of many different reasons. Then we need to really accommodate these changes. And also facilitate the reuse and the reusability of the modules that we are creating. Okay, so we want to create a system by reusing already implemented systems or modules, but as said last time, reusability is not something that happened by chance. It's something that must be carefully designed. Okay. So, as the architecture for building construction is expressed in terms of different views, and then we say plumbing, electrical, and structural, and so on and so forth. Also, the software architecture is expressed in terms of different view. Okay, so first of all, we have the structural view. Okay, which allow us to describe the logical breakdown of the system into subsystem that we also call components. That's something, another word which is used a lot in the literature, and that will come back often during these lectures. Okay, so a subsystem is also called a component. And then it will also allow us to clearly define the interfaces among these components. Okay, so what type of services are required by a component, and what type of services are provided by such a component. And in order to describe this, we use UML package diagram and UML component diagram that I assume you already know from previous courses. Then there is the interaction view that describe and specify how these components interact each other at runtime. And to this end, we use UML sequence diagram and UML activity diagram. Then we also have the data view that allow us to describe and specify how the data is shared among the subsystems, and then what is the data flow among the different subsystems. Okay, and to this extent we're going to use a UML class diagram. And finally, we have the deployment view Okay, they allow us to describe and specify the set of devices on which we will deploy our software artifacts. Okay, and to this end, we're going to use the UML deployment diagram. So, how to develop an architectural model? Let's give some high-level guidelines, let's say. Okay, first, start by sketching an outline of the architecture. What does it mean? Means try to map from the main requirements and use cases. Okay, you have your requirement specification document where you already stated all the use cases and all the functionalities that the system should provide. Okay, then try to put these functionalities together, taking into account the different design principles that we discussed during last lecture. Okay, so cohesion, coupling, abstractions, and so on and so forth. And then try to map these functionalities into subsystems. Okay, so put in one subsystem, for example, all the functionality that must be together, okay, because of the cohesion, and so on and so forth. Then, once you grouped these requirements and functionalities together, try to understand what are the main components for your software system that you want to implement, okay? And put them together. They can be just boxes sketched on the whiteboard, on paper, okay? You don't need anything special here. Just group together the different functionalities and map these functionality to boxes, okay, in your paper. And then choose among different architectural patterns that are already available. And here it comes the knowledge. And so we will discuss architectural patterns in a few minutes. But once you have these boxes, okay, in your paper, so now you need to decide how you want to organize these boxes. And then start always from the knowledge. And then in particular now we want to start from architectural patterns. So let's pick one pattern that we know, we already know it works, and then let's apply this pattern to our set of boxes and lines. Then once we have this really high-level sketching of the architecture, let's try to refine it, okay, in a more detailed one. And then we have to identify how these components, these boxes that we have on paper, will interact each other, okay, and what are the interfaces between them. Okay, so for example, let's say we have a module A that must interact with the module B. Then we can draw a line in between the two, but drawing a line is not enough. The line just saying that module A is using the module B, but doesn't say what is the module B offering, okay? And in order to do that, we need to define the interface. Interface still means the set of services that are provided and required by every given component. Okay, so once you have these interfaces, then you can decide how the data and the functionality should be distributed among the various components. Then consider the use cases. Okay, you have use cases in your requirement specification document that describe how the functionalities or how the user will use the different functionalities provided by the system. Okay, and this will allow you to understand and adjust and fine-tuning the architecture and make it more concrete and realizable. And then finally, you can mature the architecture. Okay, so once you have this very high-level idea, then you can materialize this high-level idea into a component diagrams and sequence diagrams. Okay, so component diagrams will give you the structure of the system, so the set of all the different subsystems and how the subsystem interact with each other. Okay, by means of their interfaces. So module A is requiring module B and C because it is requiring to some services from provided by component C and some other services provided by component D, and so on and so forth. Okay, once you have this static view of the structure, then you can start defining the sequence diagrams, and then say, okay, whenever I click, I call a method from module A, this will interact with module B, and then I wait results from module B, and then once I get results from module B, I can invoke a new method on module C that will return a result, and then I can print it out on my screen. So stuff like that. Okay, you know how to use sequence diagrams in order to describe the behavioral aspects of the system. Okay, so mature the architecture, and by concretizing all the different folks that you had in the previous steps. Then we mentioned about architectural patterns. So architectural patterns are really important. I mean, I guess you already know about design patterns, okay, that teach you how to organize classes into your object-oriented programming program, okay. But so we want to extend the same idea to the architectural level. Okay, so then we don't talk about classes, but we talk about components. So how to organize component in order to achieve so the quality aspects that we aim at. So what is an architectural pattern? Architectural pattern is just an outline of a reusable solution to a general problem encountered in a particular context. Exactly how the design pattern is. Okay, what is changed is that this notion apply to software architecture. Okay, and then that's why it's called architectural pattern or architectural styles. Okay, these are synonyms. There are many different architectural patterns available in the literature, and each of it allows you to design a system using components according to specific set of rules and constraints. Okay, so very important things here is that all components are independent of each other as much as possible. Okay, so the idea is that a single component should be able to work in isolation. Okay, so and this will give you really low coupling. So the less number of dependencies you have, the better. Okay, so the idea is that they must be as much as possible independent and able to work into isolation. So, I'll say there are many different architectural patterns available in the literature. We don't have time and we are not interested on reviewing all of them. We are now going to discuss only few of them, 2 or 3. So the most important, well, no, not the most important in general, but the most important for this course, and also the ones that you might use and keep at hand for the next coming days, let's say. So let's start with the multi-layer architectural pattern. Okay, this is really the most used nowadays, in particular when you deal with the web application. Doesn't matter if you use frameworks to implement like Spring to implement your web application, or you use a pure Java programming language without using any other already in place frameworks. But usually what you implement, it's a layered architecture. Okay, so a layered system, every single layer communicates only with the layer immediately below it. Okay, that's very important. And then the idea is that you create a layer, and then this layer uses the layer below it, and then you can put as many layers as you want, one on top of the other. Okay, and so then a complex system can be built by simply superposing layers on other layers. Okay, increasing the level of abstraction. We already introduced this notion of abstraction. Bottom layers should provide very general services. Okay, for example, network communication, database access, they usually are at the bottom level. Then you can superpose a layer that implements the application functions, okay, which is usually determined by use cases. So at the bottom layer, very generic services. Network, operating system, database access, file system access, and so on and so forth. Then we have the application functions. And finally, at the top level, we have the user interface. Okay, so here we just listed the three levels, and in fact, this is usually referred as a three-tier architecture, because we only have three levels of layers. Okay, but in general, you might have many different layers. Okay, here we have hand layers. Layer 1, as you can see, layer 1, it only has one lollipop interface, which is the set of services that is providing to the others. It does not have any binding towards the bottom, but only towards the top side. And then we have layer 2, which is using layer 1. Instead, in fact, it has you know I guess you know the lollipop notation from UML. Okay, so the lollipop means that we are offering services through our interface, and then the other connection is the stub connection, means that we are using the interfaces provided by the other component. So we have here a set of components. Layer 1 is depicted as a component and is providing an interface which is used by the layer 2. And then layer 2 is using layer 1 in order to implement new functionalities that are then provided to layer 3, and so on and so forth. Okay, then in this way we can create many different levels of abstractions, and every single abstraction is only relying on the layer immediately below of it. So how to concretize this? Yes, said before, the typical layers in application program is called three-tier architecture, because it only has three levels. At the bottom level, we have general services, operating system access, database access, and network access. Then we have application logic in the middle, and then finally we have the user interface on top. Then, as you can see, the user interface will never access the database directly, but the user interface can only and must only access the middle layer, okay, the application logic, because the application logic is the one providing the good abstraction to the user interface. Okay, so never break this. Well, that's not true. Never break, but in general, the idea is that you have to never break this structure. This type of architecture provides us a very good properties, as it follows a very nice set of design principles. Divide and conquer that we discussed last lecture. Because every single layer can be independently designed and implemented. So then you can split the big architecture into a set of smaller subsystems, which are the different layers, and then you can implement every single layer in isolation. You have a high cohesion because well-designed layers have layer cohesion. So all the different functionalities that are related to each other, closely related to each other, are kept in a single layer. Okay, for example, all the functionalities for database access are on the bottom layer. All the functionalities provided by the single the application logic is implemented in the middle layer. Whole functionalities provided by the user interface are in the top layer, and so on and so forth. You have low coupling because well-designed lower layers do not know nothing about the higher layers. Remember that we have information hiding. Okay, and only the connection between the layers is through the API. Okay, so then you have only one connection between layers. That's why allow to have low coupling. Provides you a lot of abstraction because you don't need to know the details of how the different layers are implemented. Okay, you just know that there is a layer. It's a black box, and then you use it because of the API. Improve their usability because lower layers are often designed generically, okay? And then you can reuse, for example, if you have the bottom layer with data access and file system access, then you can reuse this layer in many different projects, okay? They are not specific for a given application. And they also provide a lot of reuse because you can always reuse layers, okay, built by someone else. Okay, you can buy a layer and then just deploy such a layer into your application. So another very important design pattern, architectural pattern, is the so-called client server. Okay, so the idea is to split the application into two separated architectural entity. One is the server, okay, and the other one is the client, as you can see from the picture. The server is the one that is waiting for and then handling connection. Usually you have this client server application in a distributed way. Okay, you have your server running on your cloud infrastructure and the client that can be run on your laptop, for example. Okay, usually the client has implements some functionality himself, but needs the server in order to get other functionalities. Okay, so then you have your client deployed on your system. For example, can be I don't know, the Slack client. Okay, and then the Slack client will connect to the server, the Slack server, in order to send and receive messages from the others. So the client is the one that initiates the connection, okay, towards the server. So whenever you have a message to send to me or your other teammates, you write a message on your client, which is deployed on your device, and then the client connect to the server, send the message to the server, then the server will compute the message and deliver the message towards all the others. A similar architectural pattern which extend this idea is the peer-to-peer pattern. You might also know about this. I guess you used peer-to-peer application for gaming or for downloading files, movies, books, or whatever. It's very important. It's very nice type of architecture because it allows you to completely decentralize the application logic. So the difference with respect the previous one is that here we don't have a single, we don't have the server, but all the clients are both clients and server. Okay, and that's the difference between the peer-to-peer and the client server. However, in order to make the system working, because I mean here the problem is that how can client 1 get in touch with client 2 and client 3 if they are completely decentralized and then they are deployed somewhere in the world? So what we need is a server, okay, which is called lookup server. We usually interact to the server, say, okay, can you give me please the list of clients that are available in the network, and then the server will provide the different clients with the list of clients, other clients that they can connect with. And then this is how it works, for example, BitTorrent or other Hemule or other type of peer-to-peer system that you might use. So also this pattern provides a lot of good characteristics. Still divide and conquer, because allow you to divide the system into clients and servers, and you can implement them separately. I'm talking about both client server and peer-to-peer now. Okay, so the set of characteristics are essentially the same. You have cohesion, because usually the server provides cohesive services to the client. I mean, you have all the services deployed at the server side, and some other services implemented at the client side. Oh, something that I didn't mention. So you might have two different type of clients. You might have thick clients or thin clients. So thick clients means that they are just an interface, and then they use all the services provided by the server. Okay, so all the business logic is implemented server side, and the client is just an interface in between the end user and the server. Okay. On the other hand, the thick client so has some functionalities implemented within the client itself, and some other functionalities implemented on the server side. Okay. But well, the idea is essentially the same. So then, when we talk about cohesion, thin clients has everything implemented server side, and then you have a cohesion in that sense that all the services are cohesive in the server side. And when we talk about thick client, then you have cohesion because you have those services that are directly provided by the client on the client side, and all the other services that are cohesive in the server side. Okay, then you have a separation of concerns here in that sense. Coupling, I mean, there is only one communication channel used by the client and the server to interact with each other. Okay, then so the dependencies is very number of dependencies is very low. High level of abstraction because you can separate distributed components and whenever you split your architecture into distributed components, this provides you good abstraction. Okay, you have a server abstraction, client abstraction. You can reuse. Okay, it's always often possible to find suitable frameworks on which to build a good distributed system. And this is, there are plenty out there. However, these client-side systems are often very application-specific. Okay, you might find one framework to implement one specific type of computer of client server. Okay. Well, on the other side, there are many different frameworks to build generic web application, and I guess you are quite familiar with this. For example, Spring, or there are many others. Another interesting architectural pattern is this pipe and filter. So the idea is to create a stream of data, and that this stream of data is passed through a series of processes, okay? And each of these processes, each of these components is able to transform the data in some way. Data is constantly fed into the pipeline. Okay, here you can see we have the example of microphones. Okay, you have microphones. And then the idea is that you constantly feed your data into the pipeline, and then the pipeline step by step is able to transform the data from the input down to the output. The process works concurrently. Okay, that's very important, and that this type of architecture is really flexible because components could be added, removed, replaced, reordered. Okay, so you just it's like implementing a Lego system here. You can attach and detach and compose these different components as you like. Also, a lot of good things. Divide and conquer. You are able to separate the processes can be independently designed because of this separation of concerns within components. All the processes that you have that you create have functional cohesion because every single component usually provides one single functionality. Okay, so single responsible. Every single component has a single responsibility. Coupling, the process have to only have one input and one output. Okay, you cannot have different type of inputs or different type of output because the data must flow through the pipe. Abstraction is very good because so the pipeline components are often good abstraction because they only implement one functionality and they hide all details. A given process can often be used in many different contexts. Okay. And every single component can be reused in many different contexts and pipelines. So let's now discuss, introduce the last architectural pattern, and then we can have a break. So this is also very appealing and used extensively used nowadays. It's called service-oriented architectural patterns. So the idea is to organize an application of a collection of services. Okay, so a service is a component, Okay, and a component should be deployed, okay, and accessed through internet. So it's a sort of, well, it is extend the client server idea, but the server must be implemented as a web service. Okay, it's a service that is accessed through the internet. It's very nice because you have a lot of web services already available on internet. So a web service can be Google Map, for example, is a web service, or Gmail is a web service, or the Google search engine is a web service. They are already deployed. You, of course, you can create your own web service and deploy your own service. And then these services provide an interface, and this interface can be used by someone else. Okay? So here the idea is that you can create this custom web service in the middle. Okay, has a composition of different web services already deployed, well, already implemented and deployed and available on the market. Okay, so you can compose your Google Calendar service with another service, for example. Okay, and then you of course can use also your own local service and in order to create complex services that you can provide to your web client. And web client can be your browser, simply. Okay, so you can create a web service where you compose different already available services and in order to provide something more complex. These services generally communicate with each other by using standards. Okay, you have XML if we talk about web services. We have JSON if we talk about RESTful web services. But you can create your own interface. These also provide good characteristics, still divide and conquer, because the application is made of independently designed services. Remember that these services can be developed by someone else and deployed and managed by someone else. Okay, they are already there, they are available, you just use them through the interface that are provided. Okay, for example, through the Google API, if we want to use the Google services. Cohesion also is very high. Usually these web services are really structured as layers and generally have a good functional cohesion. They allow you also to increase the coupling, because these are inherently loosely coupled, okay, built by binding together distributed components. Okay, you don't know how these services are implemented or are deployed or are managed. Okay, you only know their endpoint, which is an IP address, and the set of public methods that are provided through the interface. A web service is a highly reusable component. In fact, they are there. They work in isolation. Doesn't matter if they are used by one client or by 1 million of clients. Okay, they do not change. They are really high reusable. How many people use daily Google Map or Google Calendar, for example? These web-based applications are built usually by reusing many of these existing web services. Okay, so they are there. Obsolescence, that's something that we didn't talk about so far, but is very important when talking about web services. These services can be replaced by new implementation without impacting the application. I mean, you never know what Google developers are doing behind the scenes. I mean, you don't need to, I mean, if you are a Google Calendar user, you don't need to change your application because everything is made transparent. Okay, so they fix bugs daily, they improve their own code and their own hardware infrastructure daily, but that's something that does not concern you as a developer. You just use their services, okay, without taking consideration of what they are doing behind the scene. Okay, so we described a bit what is an architecture, what are the main entities defining architecture, and some of the architectural patterns. Note that these architectural patterns can be combined together. Okay, so for example, going back to the client server. So when you have the client server here, the server can be implemented by exploiting a layered application. Okay, you might have the application logic and the database access implemented on the server side, and the user interface implemented on the client side. So in this case, we are combining a layered architecture with a client server architecture. Okay, that's very important, and that's what you usually do every day when you create a web application. You have application logic and database access on the server side, okay, deployed somewhere on the cloud, and then you have your user interface on your browser, okay, implemented by means of JavaScript, for example, or by means of HTML5. Okay, then we have two different architectural patterns combined in order to provide a better, even better architecture. But this, I mean, doesn't prevent you to have this layered architecture implemented as a standalone application in your PC. Okay. And then you can also combine this layered architecture with the pipeline, for example, where every single component can be implemented as a layered architecture, or with the client, with the service-oriented architecture, where every single service can be implemented as a layered, according to a layered architectural pattern. Okay, so let's have a 10 minutes break, and then we go further. Okay, so let's go further because we still have a lot of things to discuss and time flies. So how to make your architecture? So let's give some hints and how to make an architecture. So let's suppose we have a software system, okay? Of course, we still don't know what type of software system have, but we have the set of requirements, okay? So first hint is to, well, use the three-tier application architecture, as we discussed before. That's a good starting point. And then we split, when we divide horizontally into layers by taking into account the different technical aspects, okay? So we're going to have a persistence layer, for example, where we put all the data. Then we're gonna have an application logic where we will put all the different functionalities provided by the application, and then we're going to have the presentation layer where we usually put all the functionalities that are related to the user interface. Okay, still you have your own set of functionalities described in the requirements specification. Start mapping these functionalities with respect to these three different layers. Okay, but then this might not be enough because you're going to have all the different functionalities into the presentation, many different functionalities into the application logics, many different functionalities into the persistence or any other low-level service layer. Okay, then this is not enough. What you should already also do is to split vertically and then divide vertically the architecture into slices, okay, by considering the domain-driven aspects of your application, okay. If you have contracts, then you put all together, that's for the sake of cohesion, okay, then try to slice vertically. Everything concerning the contracts should be in one part. All considering everything concerning customers in another slice, or everything considering users in another slice, and some common stuff on the other side. Well, this is just an example. Of course, the vertical slice depends on the specific domain that you are addressing when building up your application. Okay, but in this case, you have the presentation, the application logic, and the persistence concerning the contracts. And then you have presentation, application logic, and persistent concerning the customers. And same for the users and for the common stuff. Then in this case, you can already see 12 different packages, let's say, or 12 different modules or 12 different components, okay? One for each square that you can identify on this figure. Then, once you have this set of components, then you can define the different dependencies, okay? How every single component interact with the other components horizontally, and how they interact with the other components vertically. Okay, for example, so given presentation component might interact with other components in the same level, okay, in the same layer, but they might also interact with some components that are on the bottom layer. Okay, this is the first step. I mean, if you reason in this way, then you can easily understand how to split the architecture in different subsystems and how these subsystems can interact each other. Okay. This procedure, by the way, can lead to have a high complexity. Okay, suppose we have this set of components. Okay, so then if every single component needs to interact with other components, so what we have is something like that. Okay, and then this is called the dependency architecture, and this will degrade. Okay, and together with the dependency architecture, also the ability of the software to be maintained will degrade. Okay, suppose you need to make a small change on one of these components, then this change will affect all the other components that are connected with this. Okay, that's why it's very important to keep track of the different set of components that you have in your application and the different type and number, I would say, of dependencies that you have within the architecture. Okay, so when after you made the different slicing and then you have the components, so beware on how you connect these components. Remember the low coupling and remember the high cohesion. Okay, this picture will allow you to have high cohesion, but then the next step is to keep the low coupling. Okay, because if we end up in a situation like this, then we have high cohesion, but we don't have low coupling, and then the software architecture quality degrades fast. There are some symptoms, okay, that we should take into account. So if the architecture degrades fast, then we might have to face rigidity. Okay, this means that the system will be very hard to change because every small change will force you to make many other changes because of this high degree of coupling. The architecture might result really fragile because changes cause to the system to break, okay, in conceptually unrelated places. I mean, you make a change and then you suddenly notice that you have other problems, and then you start fixing problems here and there, and then so the system will not work anymore. That's why it's really fragile. You might need to face immobility. Okay, that means that it's very hard to disentangle the system into reusable components. I mean, if you have too many dependencies in between the different components, it's very difficult to reuse only one of them. Okay, and then if you want to reuse a specific components, you also have to reuse all the others, because otherwise that specific component is not able to work alone. And viscosity, I mean, doing things right is super hard, and on the other case, making mistakes is very easy. I mean, if you don't have a clear understanding of your architecture and your application, it's very easy to make mistakes. And then finally, opacity. So the architecture becomes very hard to read and to understand. Okay, and does not really express well its the intent that were in your mind when you designed it at the beginning. This is called software architecture erosion. Okay, what is it in particular? That were these are the symptoms. Okay, this is the reason. It's called software architecture erosion. So you have erosion when you have a gap in between the planned and the actual architecture. Okay. So you make a design as a designer. Okay, you make a design, you split your problem into sub-problems, which are that will be addressed into by subsystems, and then you make dependencies in between the subsystem, and then you provide your architectural design to the developer. And then the developer suddenly starts making some changes, adding dependencies, and then so the real architecture, the actual architecture, the one that you are implementing, will be far away from the one that you have has been designing. Okay, there is a gap, and this gap is the software architecture erosion. Okay, this occurs when implementation decisions they do not achieve the architecture as been planned, okay, or violate constraints or principles that were stated into the architecture at the beginning, okay. And this gap between the plan and architecture is understood in terms of technical debt. Okay, what does it mean, technical debt? Technical debt is something that so every time you need to fix a problem, you get debt. It's okay. It's like asking money to your bank. Okay, you need money for buying your car, and then go to the bank, and then you ask money, and then you have to pay back this money to the bank with some interest. But then you want to buy something else, and then you go back to the bank and say, okay, I need more money, but the more money will sum up with the money that you asked the step before with other interests, and so on and so forth. This is also a metaphor for the technical debt. Okay, you fix a bug, but whenever you fix a bug, you introduce some interests. Okay, let's say some. You might introduce some problems, okay, while fixing a bug. These problems will lead you to other bugs, and then you have to fix all other bugs that will introduce other technical debt, and so on and so forth. Okay. Then if we don't take care to this, this situation will explode soon. There are many different reasons for this. System knowledge and skills might not be distributed well within the different teams that will work to the system. The complexity grows faster than the system size. Okay, you might have few classes, but many different dependencies among all the classes, and so the complexity is huge, even if you have a small number of classes or packages. And then whenever you touch one class, then you have to refactor all your code base. Sometimes unwanted dependencies are just created without noticing that, because just because you declare a new type into your class or a new variable in one class, and then this create a link to some other classes, and then this create a dependency, even if you don't think about that. So coupling and complexity grow super fast. Okay, when you realize their size, usually is already too late. Okay, then we need to use some smart way of doing our development, and then we will see later on what is this smart way. Management managers consider software as a black box. They don't care about this, but it's important to know how the software is built, at least what's the structure of the software. So time pressure is always a good excuse to sacrifice structure. You always say, okay, no, I have to deliver. Okay, I will think about the structure later on. Now, the important things that I deliver the functionality that we are supposed to deliver. Okay, but this is a very bad way of behaving. Okay, so that's the technical debt, something that you don't take into consideration now, and tomorrow you will pay back with high interest rates, let's say. So your enemy is the complexity. Okay, we have to fight the complexity as much as possible. So how do that? That's the big question. So start mapping physical elements to logical elements. Okay, we have types and packages when we talk about code. Okay, they must be mapped to architectural artifacts. Okay, so you have this split at the beginning that we discussed before. When you have, so we divided the architectural into horizontal layers, into vertical slices, in order to understand what are the different components that must be included into the architecture. But component is a logical entity. Okay, then we need to map this logical entity into what? To types or classes, since we are talking about a Java program, and packages. Okay. Then first make this map all the types and packages to architectural artifacts, or vice versa. Try to have a good naming convention for your packages. Okay, don't call the packages with foolish full names. Okay, so keep the packages well organized and give them a meaningful name. Okay. Then think carefully about the different interfaces, okay, of the architectural artifacts. Okay, so what type of functionality every single architectural artifact should provide, should expose to the others. And then start working incrementally and iteratively. I said before, start with the layering, then cut the application horizontally, then add the vertical slices, if applicable, of course. If you only have one domain, you cannot slice it vertically, but usually you have different domains into your application, so you can make these vertical slices. Then define the different interfaces for every single system, okay, subsystem, then the components, and then put together, start composing these components by means of interaction. So which component is interacting to which other components, and then fine-tune the dependency. Okay, and then you can make another iteration, because you can fine-tune the layering, you fine-tune the vertical slices. You understand during the development that you can create one more vertical slice, or you can integrate two vertical slices into one, because they are, for the sake of cohesion, so they are really strongly related to each other, so it's better to put everything together, and so on and so forth. Okay, so don't stop at the first iteration. Okay, design and architecturing, as well as is part of design, is an iterative and incremental process. And remember that you are always shooting on the moving targets. So things, okay, are not stable within the design and the development. Cool. So only try to be as more flexible as possible. And in order to gain flexibility and reusability, you really have to minimize the coupling. So coupling here is the let's say it's the well, not the silver bullet, but almost. Okay, so that's one of the most important measures that you should focus on. Okay. Then, in order to minimize the coupling, we should, well, first, avoid cyclic dependencies. That's very important, and then now I show you why that's very important. And remember that this, the flexibility is inversely proportional to the coupling. So the bigger, the higher the level of coupling, the smaller the level of flexibility. Okay, so as said, coupling is really the enemy that we want to fight. And always avoid cyclic dependencies. Okay, this is a golden rule. I mean, if you have A which depends on B, B depends on C, and C depends on A, okay, your architecture is not flexible at all, because you have this cyclic dependency. Okay, never have a cyclic dependency. So, but how to measure this coupling? I mean, as said many times also during the last lecture, I mean, if we cannot measure a quality attribute, we cannot understand if we are doing well or we are doing wrong. Okay, then it's very important to understand how to measure a given quality attribute. And then, so let's see how to measure the dependency. Okay, so let's be the component dependency defined as the number of a component directly and indirectly depends upon. Well, sorry, there is a typo. That's the number of components that a component directly and indirectly depends upon. Okay, plus one for itself. Example. The component here, which is with number 6. Okay, this as it depends on the two components with number 3s, and then it's 2, but it also indirectly depends upon the three components that are numbered with 1. Okay, so the CD for 6 is 1, 2, 3, 4, 5 plus 1 for itself, and then it's 6. Okay, so the first component has 6 as a CD. Okay, measurement. Then we have the cumulative component dependency, which is the sum of all component dependencies. Okay, then we say 6 as 6 as a number of CD. The two components below, they have both 3, because that depends on 1 and 2 plus 1 itself. Okay, and then the bottom layer, they have 1 each, because they do not depend on any other components, and then they only depend on itself. Okay, then just count. We have 6 plus 6, which is 12, plus 3, which is 15. Okay, and now we can compute the average component dependency, which is just the average number of direct and indirect dependencies. Okay, so we have 6 components, and then we have a CCD equal to 15, and then we can compute the ACD, and then we have 2.5. Okay, 2.5 is well, seems to be a very small number, because we only have 6 components, but it's a huge number with respect to the total number. I mean, if you consider it in percentage with respect to the total number of components. This number will increase suddenly and exponentially when you have a big number of components. So our goal is to keep this number as smallest as possible. And then if you have cycles, that's even worse. Okay, here we have a huge number, So you can make the calculation as we said, as we did before. Okay. Now we have ACD, which is 4.33. Okay, and then with the same number of components, just adding one more interaction, one more dependency in the small. Okay, that is very huge. So we need to keep the number of dependency and then the coupling very small. Okay, here, for example, we have an ACD is equal to 2. Okay, that's better than the first one, and then I could achieve this just using this dependency inversion pattern, okay, which is very nice. Okay, then, in fact, as you can see, for example, some of the components now has reversed dependency. Okay, they are reversed. We have dependency from the bottom to the up layer. What is dependency inversion? That's very important, and we will make an extensive use of this principle. Okay. This allows us to keep the number of coupling relatively small. So the idea and the motto stated from Robert Martin is to build on abstraction, not on implementation. Okay, on the left side of this figure we have a built on implementation conceptualization. Okay, we have the main component that use 3 middle components, and they use the different details that are implemented down in the hierarchy. Okay, on the right side instead we have this idea on building on abstraction. Okay, and we don't have any more dependencies between the middle layer and the bottom layer, but here we have inheritance. Okay, we build the high-level policy on the abstractions. Okay, provided and defined as interfaces, and then we might implement with at the bottom layer. Okay, in this case we have the inverse dependency inversion. Okay, and this is it's very nice a principle, and then it is already implemented in many different dependency injection frameworks. For example, Spring. I mean, if you're used to work with Spring, it is also implemented under the knees. Okay. So how does it work? The idea is that the high-level modules should not depend on lower-level modules. Okay, they should both depend on the abstractions. Okay, high-level policy depends on the abstractions, and then the bottom layer just implement this abstraction. Okay, both the top level layer and the bottom level layer depends on the central layer. Okay, that's the idea that allow us to decrease the number of coupling. So the abstraction should not depend on the details. So the details must and should depend on the abstraction. Okay, we have the abstraction, and then we implement a detailed version of the abstraction. It's not vice versa. Okay, we are used to create the details and then to abstract them. But now we have to have a switch, a mind switch, and start thinking on the other way around. So, for example, let's have a small example. Here we have a bottom, okay, and the bottom is capable of sensing whether it has been activated or deactivated by the user. Okay, once a change is detected on the button, then it turns the lamp off and on respectively. Okay, here we are building on the details. Okay, and then we have the issues that we are just talking above. Then if we change something on the lamp, this impact on the button. So solution should be that the button should only rely on any switchable interface. Okay, can be, I mean, in that case you can reuse the button for the lamp, but you can also reuse the same button for switching on and off your mobile phone, or for switching on and off your laptop, or whatever is switchable on and off. Okay, so then we have the buttons that refer to a switchable, generic switchable interface, and then we just implement a lamp as an implementation of this interface. Okay, that's a lamp is a specific device that can be turned on and off. Okay, that's the idea. So good software design are always structured into modules. Okay, that we say that, and then high-level modules should contain the important policy, decision, and business model of the application. Okay, which is the identity of the application, what makes your application different from the others. And then once we have this high-level policy or high-level business application, then the lower level modules should contain the detailed implementation of this mechanism. Okay, so only the mechanisms that are really needed to realize the policy. So the idea is that you can substitute the details, okay, but the policy shouldn't change. So you can change, make changes, or replace the mechanism needed to realize the policy, but not the policy itself. So Hansen stated that whole well-structured object-oriented architecture have clearly defined the layers, with each layers providing some coherent set of services through a well-defined and controlled interface. Okay, this is what we want to achieve here. Okay, and this dependency inversion principle is a good way for achieving this claim. So the idea is that we have a layer. The layer is using the mechanism layer, and the mechanism layer is using the utility layer. Okay, that's just a renaming of what we call the three-tier architecture. And then this is how to implement the three-tier application by exploiting the dependency inversion principle. Okay, so we don't have anymore the top layer that is using the bottom layer, but now we have inheritance. You see, we have the policy layer that has a horizontal dependency with an interface, a generic interface of policy layer interface, and then we have the mechanism that just implement this interface. Then the mechanism layer implements this interface and make use of another interface, and this interface is implemented by the utility layer at the bottom layer. Okay, so we just inverted the dependencies that we were introducing in the other way around. And that's it's very important. I mean, if you make use of this mechanism, you will create a very good quality software architecture. Some naive heuristic for ensuring this dependency inversion principle. So it's very easy. We only have one. So do not depend on any concrete class. Never. Okay. You must always relate and refer to abstract classes or interface. Okay, so never create a direct dependence from one class to another class. Okay, when you cross, of course, you cannot do this for all classes, otherwise you will have a huge amount of interfaces. But when you want to implement this cross interaction, cross-layer interaction, then you need to, well, use this trick, okay, and never bind to a concrete class, but always use an interface or an abstract class. And this will give you high level, well, low number of coupling. Then the other enemy, cyclicity. I mean, never have cyclic dependencies. As said before, that's really heavy. Okay, so if you have a cyclic dependency, will mess up completely your application. It's very difficult to take control over this because sometimes you just introduce cyclic dependencies without knowing it, just because in one class you instantiate an object by referring to another class, and then it is suddenly result on having a cyclic dependency. Okay, that's an example on how to remove cyclic dependency. Okay, so here we have two layers, two packages, presentation layer and the model layer, which is the mid layer. Then we have this cyclic dependency, main that depends on alarm clock that depends on alarm handler, and then we have this main to alarm handler. So dependency are okay, you don't follow the arrows when you, okay, here you have dependency, cyclic dependency, and then a solution is also now to, well, exploit this dependency inversion, okay, mechanism. So you have main that use the alarm clock implements the use this alarm handler, then the alarm handler is implemented by the alarm handler in the presentation. Okay, and this break the cycle. We will see. We're done for today. We will see next week how other interesting metrics to measure the quality of your system. So the idea is that in 2 weeks you are able to use this sonar graph tool that I introduced you last week, because that's very good tool that you should always use when developing your application, because I mean, he also provide some plugins for your IntelliJ IDE or for your Eclipse IDE if you are an Eclipse users or other IDE. Then always use it, because it will allow you to keep control over your architecture. I mean, if you make a new, if you create a cyclic dependency, so the tool will allow you to discover it and to solve it. Okay, so the idea is to keep using such a tool as our best friend while developing our application. Okay, so develop and then run the static analysis in order to reveal if there are some problems in the actual implementation or not. If there are some problems, well, fix it as soon as possible, because otherwise you will have technical debt later on. Okay, so the idea is to use this tool while implementing, not at the end of the implementation. So make make a modification to your code and then use the tool for analyzing it. If you are introducing some bad things, fix it as soon as possible. Don't wait better times, because better times will never come in this work. I mean, the times, the coming times are always worse than the today. Okay, that's all for today, guys. So if you have any question, please post it on Slack. I'll try to answer as soon as possible. And otherwise, okay, keep in touch, and we meet on Wednesday. I don't know if I will still using YouTube or Zoom next week, depending if I can access our classroom or not. If I cannot access the classroom, I will stream from my home by using Zoom. Okay? And then I will give you, of course, the link to the Zoom room. Okay. Bye-bye.